The question of how the universe started from nothing is one of the most profound, mysterious, and debated topics in cosmology, physics, and philosophy. It challenges not only our scientific understanding of the origins of the cosmos but also our conceptual grasp of nothingness itself. While the term nothing often conjures the image of an empty void or complete absence, in the context of the universe's origin, nothing takes on a far more complex meaning. To answer this question, we must explore the most widely accepted scientific theories of the universe's beginning, including the Big Bang theory, quantum mechanics, and cosmic inflation. The Big Bang, the universe's beginning from a singular point. The most widely accepted explanation for the birth of the universe is the Big Bang theory, which suggests that around 13.8 billion years ago, the universe began from a single, incredibly dense point known as a singularity. This singularity contained all the energy, matter, and space that would eventually expand to form the universe as we know it. Importantly, this singularity wasn't located within space. Rather, it was the origin of space itself. The Big Bang wasn't an explosion in pre-existing space, but rather an event that created space and time as we understand them. At the moment of the Big Bang, the universe began expanding rapidly. In its early moments, it was a hot, dense soup of fundamental particles and radiation. However, this singularity represents a state where conventional physics breaks down and our current understanding of spacetime doesn't apply. The concept of nothing, in this context, is more akin to the absence of spacetime. There was no before the Big Bang because time itself began at that very moment. The universe didn't start from nothing in the way we think about an empty void. Instead, it began from a state where the traditional laws of physics and our concepts of space and time were condensed into a singular point. The concept of nothing in physics. The term nothing is incredibly difficult to define within the context of modern physics. In everyday language, nothing refers to an absence of matter, energy, or substance. However, in quantum mechanics, nothing is far more elusive. The quantum field theory suggests that even in what appears to be empty space, there are still fluctuations of energy that constantly arise and disappear. This means that in the quantum world, there is no true nothing. Even a vacuum is teeming with activity on incredibly small scales. Physicists often refer to the quantum vacuum as a state of lowest possible energy, but it is not empty. In fact, it is an active, fluctuating field in which particles and antiparticles can spontaneously appear and annihilate each other in incredibly short periods of time. This phenomenon, known as quantum fluctuations, suggests that even in the emptiest of spaces, particles can emerge momentarily, seemingly from nowhere. In this sense, the concept of nothing that led to the creation of the universe may not have been a complete absence, but rather a highly energetic quantum state with the potential to create matter and energy. Rather than coming from an absolute void, the universe may have arisen from this state of quantum potential, where fluctuations in a primordial field triggered the Big Bang. Quantum mechanics and the birth of the universe. Quantum mechanics provides an intriguing framework for understanding how the universe might have emerged from nothing. According to some theories, the universe could have arisen from a quantum fluctuation. In this scenario, a small fluctuation in a quantum field might have been the catalyst that caused spacetime to begin expanding. These quantum fluctuations are temporary and unpredictable, but they can lead to the creation of particles and energy. The idea of the universe coming from a quantum fluctuation leads to the hypothesis that the universe did not require an external cause to begin. Instead, it could have spontaneously emerged from a quantum state where the fundamental fields of energy were unstable enough to give rise to space, time, and matter. This idea is supported by certain interpretations of quantum mechanics, which suggest that universes can spontaneously pop in and out of existence due to quantum fluctuations in what is sometimes called the quantum foam. This theory is often tied to the concept of vacuum energy, the underlying energy present in empty space. In quantum theory, even empty space is filled with this vacuum energy, and it's possible that fluctuations in this field led to the creation of the Big Bang. Essentially, the universe could have emerged from a quantum vacuum fluctuation, in which spacetime itself was created from nothing but the potential for existence. This aligns with the idea that the universe could have arisen from what might be described as a quantum nothing, a state with no conventional matter or energy but the inherent possibility for those things to emerge. Cosmic inflation, the rapid expansion of spacetime. Another crucial concept in understanding the origin of the universe is cosmic inflation. Cosmic inflation theory proposes that during the first fraction of a second after the Big Bang, the universe expanded at an incredibly rapid rate, far faster than the speed of light. This exponential growth stretched the fabric of spacetime itself, setting the stage for the formation of matter, stars, galaxies, and everything else in the universe. Inflation explains how the universe, which began as a tiny, incredibly hot and dense point, expanded to its current size. Before inflation, the universe was incredibly small, and its energy and matter were highly concentrated. The rapid inflationary period flattened out any initial irregularities and allowed for the uniform distribution of matter that we observe today. Inflation doesn't directly explain how the universe came from nothing, but it does provide an important mechanism for how the universe could have evolved so rapidly from an initial quantum fluctuation. The theory suggests that inflationary processes were governed by quantum fields, which themselves emerged from a state of quantum potential, and these fields gave rise to the universe's expansion. The beginning of time. One of the most profound aspects of the question, how did the universe start from nothing, is that it touches upon the very nature of time itself. According to general relativity, time and space are intertwined in a four-dimensional continuum called spacetime. The Big Bang represents the beginning of both space and time, which means that asking what came before the Big Bang is somewhat of a nonsensical question in classical physics. Time itself may have had no before in the traditional sense. In this way, the universe's origin isn't just a question of how matter or energy came into being, it's also a question of how time itself began. If time began with the Big Bang, then there was no before in the way we typically understand it. The universe, in this sense, began from a state of nothing, not just in terms of matter, but in terms of time itself. Conclusion: a universe from potential. The question of how the universe started from nothing is a mystery that challenges our understanding of both science and philosophy. While the Big Bang theory provides the framework for understanding how the universe expanded from an incredibly dense point, the idea of nothing from which the universe arose is more complex. Rather than a complete void, the universe may have emerged from a quantum state filled with potential, where fluctuations in a primordial energy field led to the creation of space, time, and matter. Quantum mechanics, the theory of inflation, and our understanding of spacetime all offer insights into this enigma. However, as we delve deeper into these concepts, we are left with a profound realization. The origin of the universe may never fully be understood in human terms. It's a reminder of how much more there is to explore in the universe and how little we truly know about the very nature of existence itself. The universe didn't just begin from nothing in the traditional sense. It began from a quantum potential that gave rise to everything we observe today, challenging our deepest assumptions about reality, existence, and time.